Quotient of powers property in words says that if you divide two numbers with the same base, then subtract the exponents. In words, here. In more symbolic terminology, would be if you had a to the x over a to the y, that's the same as taking that base and taking the top exponent and subtracting the bottom exponent. In symbols, it would look like this, where a is not equal to 0. In a more concrete example, it might look like this. How about 2 to the 9th power over 2 to the 4th power? That says same base. So I can, and I'm dividing them, so I can subtract the exponents. So I could say that's the same as 2 to the 9 minus 4, which is just 2 to the 5th power. Is the quotient of powers property. Okay? It's the partner that goes along with the product of powers property from yesterday.
What number would you subtract from? Did you subtract?
Note that we're in our more symbolic example here, that we're taking the numerator's exponent and subtracting the denominator's exponent. We'll always take the numerator's exponent, subtract the denominator. Also note that our answer here is no longer a fraction, or at least written as a fraction. This is implied that this new answer is in the numerator, or the top part of any fraction that we might have.
So knowing this, can you try doing
So knowing this, let's try simplifying some of these problems. So knowing this, Angela, what would you get for the first one?
What did I get?
Yep.
9 to the 7th.
Angela correctly got 9 to the 7th. Same base and division. So the exponents should now be 9 to the 12 minus 5, numerator minus denominator, which is the same as 9 to the 7th.
Also, you do letter C.
B should be what? Negative to the 4 minus 3 to the first, so just negative 2. Just anything in the first power is just itself. Oh, how do I handle... Boy, this is more complex than the first one. What should we do for... Lily, what are you going to try?
Well, first you have to do 6 over 3 plus 4. So you have to add it and top
Okay, so simplify the numerator first. So 6 to the 3rd times 6 to the 4th. Add the multiply base, add the exponents.
Oh wait, you're supposed to add. And then you subtract 7 minus 2. Yeah.
Simplify the numerator and denominator as much as you can first, and then apply our quotient rule. So our product rule still applies. So if we have multiplying the bases, we'll add the exponents. And then if we decide to then divide the same base, then we can subtract the exponents. Numerator minus denominator. 7 minus 2 is exactly 5. Oh boy. The next one has a fraction times something that's not a fraction. How are we going to handle that? Angela, what do you want to try?
Well, I'm not completely sure, but I kind of did something like that cross multiplying. So I ended up having like 1 over R13. I'm not quite sure. Like,
Cross multiply is a strategy for solving a proportion, or solving an equation. So if you're going to use cross multiply, there better be an equal sign between the two things you're cross multiplying.
I did another.
So I don't see that. Does anyone have it? Because thank you for. I want to see. I want to talk. Maybe involve other people. Did anyone have a suggestion for what we could do here? So far?
You could do like, there's like an invisible like one exponent kind of right?
Okay.
Well, it stays the same, but whatever.
Okay.
Couldn't you subtract that from the bottom and then multiply it? Or I don't know what you do. Like take the rule that we did yesterday and like it'd be like something like -4
Okay. I want to pause right there because note that if we put this 1 in there, that's good. But are those two the same base? 1 and r the same? If the bases aren't the same, then the rule we did just now and the rules from yesterday, they don't apply. They have to, in order to combine the exponents, the bases have to be identical. So I don't think that's going to work in this case. It's a great suggestion. I think there are some good things going on in there, but we can't combine those bases because they're not the same. Courtney, could you maybe help us out? You want to put a 1 over on top of the r they?
Yeah.
So I guess so if you're saying if I want to turn 2 into a fraction, I would go like this. No, what would you do? Put under. So then where do you think that 1 could go? Okay, I like that suggestion a lot. Now what should we do? Is there an equal sign? No, so it can't cross multiply. How do you multiply 2 fractions together? Multiply straight across the top and straight across the bottom. What's nice here is that what's 1 times anything? Well, just whatever we started with. So what's 1 times r to the 8th? Whatever over there. What's r to the 5th times 1? Okay. So this exponent here actually didn't come into play. So now that we've got 1 fraction, and we've got now the same base, r and r, now we can combine this. Division means, what do we do to the exponents? Subtract them. R to the 3rd power. All right. Before we flip over and look at the backside with the second property, I want to highlight. I want to kind of show you how we could have solved this a different way without using these properties. And the reason I'm doing this is because when we come back on Tuesday and we look at our next section, we're going to look at some special cases of what are some weird things that can happen if we divide and apply these rules. I'm going to show you where those things are coming from in advance. So, for example, if I wanted to solve this one, C, in a different way, another way I could have tried to simplify this would have been to write out what all those powers are. So I could have said 6 to the 3rd is 6 times 6 times 6. 6 to the 4th is 6 times 6 times 6 times 6. And that would go on top. This is an alternate way to solve, part C. The bottom, what 6 squared was what? 6 times 6. Okay, on the top is all multiplied. 6, this has got what's called a bunch of factors of 6. There's a ton of 6. And the bottom is kind of similar. Well, if I see 2 like factors on top and bottom, I can divide those. If it's all multiply, I can just divide out things in common. So, for example, what's 6 divided by 6? Okay, that's a 1. What's 6 divided by 6? Also, 1. There's no more 6s, there's just 1s down here. So let's count what we have left over. Well, 1 times 1, that's just 1. And 1 times anything is just whatever is left over, is whatever is still here. So on top, I'm going to have this expression. What's a more complex way to write 6 times 6 times 6 times 6 times 6? And what's 1 times 1? And what's anything divided by 1? Itself. Note that we got the same answer. The only thing, this didn't use exponents. Do you have to do this? No. Use the exponent rules. It's quicker. I did this because when we come back on Tuesday to reiterate, we're going to see some kind of weird things that can happen when we apply this division rule to like different combinations of exponents. And we're going to start, and we're going to hopefully draw some conclusions as far as what happens when some of those more interesting situations come up. Okay. The second property goes hand in hand with the last one from yesterday. If you recall, the last property we looked at yesterday was the power of a product. That said that if you had an exponent on the outside of some parentheses and you had it all multiplying on the inside, that you could just distribute that exponent out. Power of a quotient is its partner, and it says that well, multiply and divide are basically the same thing. They're just opposites of each other. They're inverses. So all the rules that apply to multiply should also go to dividing. It says that it says the following. In words, it says that for a power of a quotient, you can distribute the exponent to each base. Power of a quotient property says that for a power of a quotient, or if you have, in symbols, it will look like this. If you have two different numbers divided by each other, and I raise that whole thing to a power. Power of something being divided by something else. If that's the case, then I can actually distribute that exponent to each base. That's the same as a to the x over b to the x. We actually used that in the warm-up today. Say that second example that you did, it was what? It said 3 over 8 squared. Instead of writing out 3 over 8 times 3 over 8, we could have much more quickly said that this is the same as 3 squared over 8 squared, which, as you guys told me, was just 9 over 64. We have two pretty basic ones, and I have two that will ratchet up the difficulty a little bit. But it's not really getting hard, it's just really a little more work. Use the power of a quotient. So is there any adding, subtracting in here?
No.
No, so then we can go ahead and distribute this. So this should be the same as our first base over the second base. Well, the bases are different, so we can't go combining them together. The best we can do is just leave it as c to 6 or d to 6. C and d aren't the same, not necessarily the same, so we can't combine these. We can't subtract the exponents. Negative 2 over y to the 4th, that should be the same as negative 2 to the 4th over y to the 4th. That would be our answer in exponent form. I claim you can actually, that negative 2 to the 4th is actually a reasonable number that you could rewrite. Negative 2 to the 4th should be negative 2 times negative 2 is 4, positive 4. Positive 4 times negative 2 is negative 8. Negative 8 times negative 2 is, what is that? Negative 8 times negative 2, positive 16. You could equivalently write this, you could simplify negative 2 to the 4th. I claim that's a reasonable number. 16 is not too bad. If you left your example in -2 in parentheses to the fourth, I probably wouldn't take up any points there at this level. But before the bell rings here, I want to make sure we at least look at one of these more complicated ones. Let's look at the first one here. 3a to the fourth over b to the fifth, all that to the third power. You could write all these things out, or you could write this times itself 3 times, or we could just apply our property. Is there any adding or subtracting going on in here? No. So that means this power of a quotient property applies. That means that every single base in here, and I see 4 of them, we can distribute this third power to. 3 is a base. This A is a base. That 5 is a base. And this B is a base. Yes. So if I distribute this exponent out to every single base, 3 to the third, 5 to the third, A to the fourth to the third, B to the third. Some things you can simplify in here. Hopefully this is jumping out as something to be simplified. A to the fourth to the third, power of a power is multiply those exponents. There's no common bases on top and bottom, so the best we could do is then you could go through and figure out what 3 to the third and what 5 to the third is. 3 times 3 is 9, times 3 is 27. 5 to the third is 5 times 5 is 25. 25 times 5 is 125. This would probably be okay. If you get more than like 4 digits, now we're thinking just leave it. Okay. The last one. Let's see if we can get the last one in. I want to. Let's see. I see power of a power. There's no adding or subtracting, so we can distribute this 7th power. Say x to the. Let's see. 3 times 7 is 21. Y to the first to the 7th is what? Y to the 7th. Times 1 over 3x to the 8th. When I multiply straight across. So let's see, x to the 21st times 1 is x to the 21. Is there any like bases on the bottom? No. So I could write this as what? 3 x to the 8, y to the 7. Just combine them together. Are there any like bases on top and bottom?
Yeah.
The x's. Okay. So now you get what? What's x to the 21st divided by x to the 8th? Okay, same base divided. Same base divided. What do I do to the exponents? Subtract them. So then let's see. X to the 21 over x to the 8. So 21 minus 8, I believe is to the what? 13? When we subtract the same bases, we'll put our answer on the top of the numerator. Subtract same base top, answer goes to the numerator. What's left over is the 3 and the y to the 7. Those stay on bottom. Okay.